Professor Ralph Johnson from the University of Illinois at the Garden of Champaign. Most of you already know part of his work. Professor Johnson has done work in the last 30 years that changed the way that we see software development. He has done extremely high quality work on frameworks and based on design patterns and refactoring and in general software design that influence the way that millions of programmers work every day nowadays. Other countries. He was one of the authors of the Design Patterns book, which is the book that maybe the computer science book that sold the largest number of copies in the history of computer science, and also influenced the way that millions of people work and develop software today. So, thank you very much for being here. You tell us about the 20 years of Design Patterns.
So it's been 20 years since the book Design Patterns came out. If you look at the copyright on it, it actually says 1995. One of the things I learned from the book was that publishers often will try to put a later date on it than it came out. So it came out in October of 94, and they wanted to put this 95 date on it because usually technical books only sell for 2 or 3 years. And so by having a 1 year later book, you can make it sell a little bit longer. It seems new longer. And it's a very standard. Often you'll be able to buy a book, and when you buy it, if it's really new, you'll see that next year's date will be on the copyright. That's just a little trick I learned from our book. Well, of course, 20 years shows it wasn't necessary to play this trick with our book, but it's actually very, very rare for a technical book to keep selling for 20 years. The book, so that by itself is a sign of how influential the book has been. But in fact, there have been lots of different awards that the book has won. Now, one of the things, again, I learned about awards, part of the reason the book has won so many awards is because the other 3 authors were all at IBM. And there are people at IBM that want IBM books to receive awards. Or you need to have friends. To get an award, you must have friends, because these friends have to nominate you, and they need to be people on the committees that choose. If you're IBM, I mean, there's somebody from IBM on like every single committee having to do with computers. So that's an advantage of having a big company. So that helped. But in fact, the book has been very influential, and things like the Jolt Award and the Dr. Dobbs Journal, those are industry awards that happen just a year or 2 after the book. But again, the reason for this, the book had a lot of people talking about it. It sold a lot of copies right away because so many people were talking about it. Now, part of it was we did some things mistaken. I mean, by accident. We didn't plan this, but it turned out to be the right thing to do. Having the book out, the web had not been invented yet. Okay, so you can't really say we put it on the internet. We had an FTP server, and we had PDF hadn't been invented yet, so we were using PostScript. We had PostScript files, PDF on an FTP server, and we had a mailing list. You could join the mailing list. We had about 500 people on the mailing list, and every time a pattern would come out, we would be discussing it for a couple of weeks. And that, again, a lot of people knew about the book. They would tell their friends. There also were people like Kent Beck and Grady Booch were talking about the book, and all those things made it. That's one of the things I realized. This is actually a lot of good books that don't make much of a splash. And so one of the things I've learned from this is to try to share what happened to me with other people. I see a really good book to try to promote it to make sure that it gets big. But our book had a big impact. So what is the book? Actually, before I get that, another impact of the book is that there's a lot of books that in some sense are takeoffs on it. That's another part of the influence. So some of the books are very specifically about design patterns, about the exact same patterns that are in our book. They're covering the same material from a slightly different point of view. Now the book has a lot of code examples, mostly in C++. Some of them are in Smalltalk, some of them are in C++. But what we thought would probably happen was people would write versions of the book for other programming languages. And one of them, the very first one, was a group of people, again, from IBM. that were writing about Smalltalk and showing how the different patterns showed up in the standard Smalltalk libraries. And it was a very well-written book, but I started to get a hint, and I knew these people beforehand, and they were very prominent people in the Smalltalk community, but one of the things I started getting an inkling of future problems, whereas we were reading drafts of the book, they made some serious mistakes along the way. We had to correct them. Like, if people who are this smart and this experienced are making mistakes, what are average people going to do? And I'm going to tell you some of the stories about that. A very recent book, and this book now actually sells more copies than Design Patterns does. I think now by maybe a factor of 2 or 3. It's Java, uses Java. And how many people have seen Heads First Design Patterns? Some people, well, a lot of people have read it. But it's a very well-written book aimed at younger people, I think, the sort of style that it's written at. One of the things I say, even though I admire the book, and the people who wrote it really understand design patterns well. I could never write that book, and I actually find it a little bit annoying. I'm a different generation. The book is written for younger generation people, and I'm not the target audience for it. So, in general, that's the way I feel about all the Heads First stuff. It's written for somebody else. It's not written for me. But it's very important to have books like that written, and that's a sign of success is when people are taking the material and using it in lots of different ways. But I'm perfectly happy with people who read this book, and then maybe read Design Patterns or maybe not. I mean, I think that's perfectly fine. Now, these other books, there's a lot of other pattern books, which are different patterns that are in Design Patterns. Design Patterns was never intended to be complete. We never said that these were all the patterns there were. These were just some patterns, and that we were saying that if you don't know these patterns, it would be useful to know them. There would be good things to learn. So one of my favorite patterns books is Domain-Driven Design by Eric Evans. How many people have seen Domain-Driven Design? Okay, that's good. There's a number of people. Parts of it are, you might say, the same low-level design issues of design patterns, but a lot of it is more about architecture, and it's about how groups of people work together, how you decompose a bigger system into smaller parts so that you can have multiple teams working together to solve it. There's a lot of very interesting architecture issues that are in that book. Not hit the screen. And then Martin Fowler, of course, has written many good books. And several of them are patterns books. So this one, Patterns of Enterprise Application Architecture, is useful if you're building a modern, object-oriented business system, connected to the web, talking to relational databases, that sort of thing. And there will be a lot of patterns that his book will describe. Now, and the books actually are sort of related in that a project could use patterns from both those books pretty well. And the Hillside group keeps web pages with lots of patterns books. There's actually so many patterns books today that it's hard to keep a complete list of them. And you'll see them, there's a lot of them for user interface design, for parallel programming, for real-time embedded systems. There's Ajax pattern, so you want to learn. That's one of the things people have discovered, is if you want to teach people a particular style of programming, that figuring out what the key patterns are and then describing those patterns is a good way to teach people things. And so we see patterns in a lot of areas. And sometimes people ask me questions like, well, your patterns are about object-oriented programming. What about functional programming? How do your patterns work for there? And I'll say, our patterns are different, and they're not the patterns of functional programming. And I'll always say, and I wish those functional programming guys would get their act together and write a good book about functional programming patterns. Because that's one of the number of areas where there isn't a book. But like I said, one of the things that I'm happy about the effect of our book is that it's influenced lots of other people to write books, and I learn a lot by reading their books. So that's why it's good. Now, what is Design Patterns? Well, it's a catalog. It's a catalog of 23 different patterns that are things you might see in object-oriented design, 23 design techniques. Now, my brother does a lot of woodworking, and he's got a number of books that help teach woodworking. And typically, they will be catalogs of techniques. And I remember one of his books, every technique was 4 pages. There would be a name for the technique. They would show a table or a chest of drawers or something you would make and show how that pattern was in it. They didn't call them patterns. I don't remember what they called them, but it's the same idea. And then they would show how you make it. First of all, they would show what its advantage is, and then they would show how to make it and how you hold your hands when you're pushing the chisel or whatever you do when you're making these things. So this idea that when you're building something, there are certain techniques that you use over and over in many situations, and it's universal. One of the books that influenced us was by Christopher Alexander, who was writing about patterns in buildings. And so this idea that it's useful to have names for these things that you see over and over, and to try to... So having these, the ones we picked, we chose them because we saw them in many, many object-oriented systems. Usually they weren't documented. Some of them actually had been documented in a few places, but most of them were not documented. Most of them did not have names, so we had to give names to them. And having those names gives us a vocabulary. The vocabulary is the patterns. We can talk about our system by describing the patterns that are in it and how the patterns are related to each other. And so this helps if you're learning to program. If you're learning object-oriented design, you can look at the book, you can go through each one and say, do I know this? And you may know it already. You may say, oh yes, I did this, I've seen this in some system, or maybe you've never seen it before. If you've never seen it before, you can say, well, I'm going to practice it. You can read a program that uses that pattern and try to understand it. You can put it into the next program you write. Usually if you do that, half the time that you put it into the next program that you write, you'll do it wrong. That's what happens the first time you do anything. You usually do it wrong. It's okay. Sometimes people say design patterns are a bad idea because look at all these programs out there where people use them wrong. Well, that's like saying programming is a bad idea because look at all those programs out there where people put bugs in their programs. People, when you're learning something new, you'll make mistakes, and we should, partly when you're a company hiring people, you want to make sure you don't have too many people who are new. But the other hand is that we have to live with that. And it's good in school to be practicing, get your mistakes out on class projects and games that you're writing before you start writing important things. But because so they're useful when you're learning, they're useful to talk with other people about your designs, and it's been very helpful in the object-oriented community to have these words. We can talk about our designs. It means that communication is more efficient, and conferences, what people talk about at conferences changed after the patterns became a standard. It can also help you when you're designing, even as an expert. You're working on a problem and you get stuck. You don't know what to do. You can say, well, maybe this pattern would work. You go, no. Well, maybe this pattern would work. No, that wouldn't work. Maybe this pattern. You try out different things in your mind, and then you'll often will discover something that will work. Just as having sort of a checklist of things to go through. The more possibilities, the more ideas, techniques that we can use when we're designing, the better. And so they're not magic. Often, when you try to use a pattern, you can see that it could be used, but when you think about it, or if you try it out and then look at what you do when you're done, the pattern makes your system worse. It doesn't always make it better. This is just a catalog of ideas. And yes, they're common ideas. That means there's many times when they're useful, but that doesn't mean they're always useful. Now, when we wrote the book, we put the patterns into 3 categories. We called them behavioral, structural, and creational. Now, the creational category is a pretty good category. You can tell every pattern whether it's creational or not. But I don't think that structural and behavioral are very good categories, because there's many patterns where if you just look at the pattern and say, is this structural? Is it behavioral? It could be put in either category. There's not sharp divisions. Some years ago, the four of us got together to talk about doing a second edition. And one of the things we really didn't like about the first edition was our categories. Because the structural behavioral is just not a clear set of categories. And not very useful either. If you're trying to design, the reason we had these categories was because when we were writing the book, we have a list of 23 patterns. 23 is a very long list. You know, nobody wants to see a list of 23. So try to break it up into smaller lists so we can have a number of smaller lists. It'd just be easier to think about. At one point we had 6 categories, but one of the categories didn't have any patterns in it. And that was stupid. So we come up with a different way of categorizing. I mean, we played around with it and finally ended up with these 3. And of course, we're trying to get the book out the door. We need to publish. There's deadlines. And so anyway, it was good enough, so we published it. But thinking about it, now what we decided was that a better way of categorizing would be to have core patterns. In other words, the patterns that people use a lot. And then we had peripheral patterns that people didn't use too much. And then there would be composite patterns, or compound patterns, which are patterns that are sort of made up of simpler patterns. And then the creational pattern. We'll keep the category of creational patterns because that's a pretty good category. So that's what we decided. This was maybe 8 years ago when we had a meeting and decided this. We've also people want to know what new patterns would you put in. If you do the book again, what other patterns you consider are equally important. And so I'm going to go through patterns, and when you see the italics means a pattern that's not in the book. So if you look at that and say, I didn't think that was in the book. You're right, it's not in the book. But these are patterns that we thought would be worthy of being included that we like. Now, so this is the core patterns. One of my favorite patterns, and it's, people are like, what's the most important pattern? I don't know what the important pattern is. Different patterns are important in different projects, but one of my favorite patterns is composite. And the reason I like composite is because there's been many designs that I've worked on, and I would, as the design would change over time, I'd try to make it be more reusable, usually, that I would figure out how to make something be the composite, how to get the composite pattern into the design. And that seemed to be a turning point in the design. When I was able to do that, suddenly the design seemed to be more composable. Composite seems to go with composable, but it really seems to do that. And again, I have no scientific proof. I can't tell you exactly why that is. I can give you some arguments about it, but it's really more of a feeling than anything else. And there are other people who have other favorite patterns. It's not like one best pattern. But so what is the composite pattern? So the idea is that we're going to have some sort of a tree of objects, and we're going to be able to have an object, what we call, there's a lot of different types of things that can be in this, so they're all components, lots of different kind of components, which we're going to plug together to make big objects. And we want to be able to treat a group of objects like a single object. So we want to have a single object that represents the whole group. And a typical way this is done, and this is not the composite pattern, this is getting close to the composite pattern, but it's not the composite pattern. But so a typical way it's done is that we'll say we have a component class, and there's different subclasses, but every component can have a list, can have a collection of children. So a component can have children. And so the children can also be components, so they can have children, and they can have children, and you get sort of a tree of objects. Now, the problem with this is that, obviously there's many leaves to a tree. But some of the classes are always leaves. You never are supposed to have children. They're never supposed to have children. And what you'll discover is that if you build your system and you start teaching other people to use it, that they will frequently make the mistake of giving some object that should never have children, but they'll give it children. And this design doesn't prevent that, because you say every component can have children. Now, the first time I ever ran into this was in Smalltalk with the original model view controller, and every view could have subviews. But in fact, you could have a button view or a paragraph view. They really should never have subviews. And people were frequently making these mistakes, and there are certain standard problems that would occur whenever they did that. And I got to the point where I could debug people's problems with their GUIs. So they were doing graphical user interfaces. But again, this is like in the 80s, maybe 1990, the very early 90s. So this was before the days you could do screenshots and email a picture to somebody. It was nothing like it. It was all, email was only text. Email. I could debug people's graphical user interface by email because they all did the same mistakes over and over and over again. They would complain, and I could tell them, I bet you gave your button a component. The buttons aren't supposed to have subviews. And sure enough, that was the problem. So the composite pattern, the real composite pattern, is a little bit different. Yes, you have a component class. But now you're going to categorize your subclasses. Some subclasses we call leaves. Other subclasses we call composites. Now there might be only a single composite subclass. There might be 12 composite subclasses. So the pattern, don't read it like a standard UML diagram where you're thinking there's only two classes. It's really two kinds of classes. You've got the leaves and you've got the composite. And a composite will have a pointer to have a list of children. It'll have a collection of children. But you don't say that every single component does. Now, one of the things about the composite pattern is that we really want all these objects to have the same interface. We want all these types, or the different classes you make, to all have the same interface. And there's certain problems that arise. So one of the things you want to be able to do is to enumerate your children. Now, that turns out to be pretty easy. Even if you have a leaf, you can ask the leaf, what are your children? And it says, I don't have any. That's easy. You can ask for an iterator. It gives you an empty iterator. You get whatever. So that's pretty easy to say that a leaf will act like a component. All components have a way of iterating their children. Yes, we can do that. And so that's easy. But you want to be able to add a child. Well, that gets to be difficult. Now, sometimes you'll have a design where you only add a child when you create an object. So then the constructors would take a list of children, but you would never add one any other time. But often you can't. Sometimes you have to be able to add them. And then you always have a problem of what do you do? Because you really can only add a child to a real composite. You can't add a child to a leaf. How do you do that? Then the book talks about the issues in there. That always becomes a tricky part of implementing your class library. And after you've done it a couple of times, you just realize, yes, composite always has that issue. I've had people who read the book, and they replied that they were really happy to read about the composite pattern because they thought they were stupid since they couldn't solve this problem. There was like no perfect solution, and that's what we say. There is no perfect solution. It's something you have to wrestle with every time you use the pattern, and it's good to know that. It's good to know. It's just sort of like it's nice to know about undecidable problems, because you can spend a lot of time trying to write a program to solve an undecidable problem. And when you take a class and you learn about all this theoretical stuff, it seems very mathematical, not very practical. But the first time somebody tells you to write a program and you say, nobody can write that program, that's a big advantage, and you realize that's actually useful. Okay. Does anybody have any questions about the composite pattern? And how many people use a composite pattern? So know that you've used it sometimes. Yeah. And I bet a lot of others of you have, because if you're doing graphical user interfaces, there's always contains that hold smaller things, and that always turns out to be the composite pattern. So look at what you're doing, and you will see that you've been using it. So another one of the patterns that's in the core set of patterns, gets used a lot, is the observer pattern. Now, the observer pattern is very, very common in graphical user interfaces. And some people think, well, it's just a user interface pattern, but actually it's not. It is a general pattern, and the book describes the more general aspect. The characteristic of the observer pattern is that you have some object, the subject, that has state, and it will change. And then you have other objects, the observers, that need to know when it changes. So they have to be notified. And the way it works is observers will register. They will tell the subjects, add me as a dependent, or I want to register for these events, I register for this update. And then, when the subjects change, they will, the subject will know, somebody will know. When the subjects change, the observers are notified. And they're always notified by a pretty simple interface. And so here I'm calling the interface update. So when the subject changes, the observers get sent the update message. When you, but part of, actually this is an interface in Java. This would be an interface. In the book, of course, uses C++, and so there's no such thing as an interface. We have sort of pure abstract classes here, but with a subject, there's going to be some behavior because you want to be able to add a dependent to register. That's what add dependent register is the same thing. Remove a dependent or unregister yourself. And then to notify, to say the subject has changed. When the subject has changed, all the observers get updated. Now, the way this gets used in practice is that you make classes that either are subclasses of subject that are going to be subjects, or you make classes that are going to be observers. They're going to implement the observer interface. And this is sort of an example of simulating some 1920 era Chicago mobsters. And you've got the FBI agents who are out there spying on them, trying to catch them in the act of robbing a bank or whatever other illegal activities they'll be doing. So the mobsters will have operations like rob a bank or drive the getaway car. Those are their operations, and they don't actually know. They don't actually know. This is part of the observer pattern, is that the mobsters don't actually know if there are any observers. And of course, there could be other kind of observers, like there could be junior gangsters who are trying to learn how to be a really good gangster by watching them. Those would be other kind of observers. Right? There's a different type of observers, but the ones they would worry about are the FBI agents, but they can't actually tell whether there are any FBI agents who are observing them. Now, the FBI agents know whether they're observing mobsters or not. They don't necessarily know what they're going to do, be able to predict what they're going to do. The way this gets programmed, though, is very funny. If you look at an implementation of the observer pattern, and it's implemented everywhere, it has different names, like Microsoft, I call it publish, subscribe, for example. But the way it always works is that when we look at our concrete subclasses, an FBI agent has a pointer to a mobster. Mobsters don't seem to have any pointers to anyplace else. But they inherit some implementation. They're reusing some implementation. And part of this implementation is that it keeps a list of all the observers. And that when we say, mobster, rob a bank means change state. And we change the state, that's going to notify all the observers. At runtime, if you have a debugger, you can look at your code, you can see, oh, there's a pointer here to there. At runtime, there are going to be a list of all the observers that a subject has. And when you notify, perform an operation on a subject, and it does the changed operation, it will run over all the observers and send them an update message. So it's sort of funny because, again, we know that it's silly to think that a mobster has a list of all the FBI agents that are watching them, but that's what happens in a computer whenever you do a observer pattern, and it happens all the time. So the thing that's very good about this pattern is that when we think of these as classes, this is an interface, very, very small interface. The subject uses that interface, but this interface doesn't really include the subject at all. The classes that you write are either implement this interface, or they are subclasses of this, or reuse it. Sometimes it's done by composition instead of inheritance. And again, this class is going to depend on that class, but there's no cycles of dependency. If you're reusing a library that performs this, there's no cycles here. And when you make this class, it really only depends on that. And this class is going to depend on both of these, but nothing else will depend on it. So there's no cycles of dependency in this. And that leads to decoupled systems, where you can have layered systems and one layer doesn't depend on the other. It has very nice compile time properties. You obviously are getting some kind of runtime coupling. There's runtime coupling, and that can cause a problem because a typical bug in a system is that you press a button here, and you expect something to happen there, and it doesn't happen. And you say, why doesn't that happen? And well, maybe when I press a button here, I'm trying to perform the changed operation over here, and maybe the observer isn't observing it, or maybe the observer was implemented wrong, so it does get the update message, but it doesn't react properly. So that it's hard to tell. And again, these are sort of classic issues in the observer pattern that you always have. But the advantage of the observer pattern is you can add new type of observers. You don't have a lot of coupling. It leads to very flexible systems. Now, this is typical of design patterns. The subtitle of the book is Elements of Reusable. There's that word reusable object-oriented design. And the reusable, well, at the time we put it in the book, the time we made the title, it was maybe a wish. It was partly because everyone was talking about reusability, and so we knew it helped sell the book if we said reusable. But in fact, we got these patterns by looking a lot of reusable software. The software itself was actually reusable, and we studied the patterns that were in it. So we were hoping that we were figuring out why it was that the software was reusable. And of course, there's more than just using a particular language, using particular patterns that make software reusable. But a lot of the patterns are about making your software more flexible, easier to change, and they really do help reusability. So I explained two patterns, a composite and a composite pattern and observer pattern. Both of those help make your software be more reusable. There are a couple more patterns that we thought could also be considered core patterns. We didn't have them in the book. So I wanted to let you know the kind of thing that we think should have been there. And so the first one is value object. So the value object pattern is different, I think, from a lot of the patterns in the book. It's not about polymorphism. It's not about implementing certain interfaces. A lot of the patterns, both these patterns, both observer and composite, are very much about interfaces and polymorphism. And not all the patterns, but many of the patterns are that way. Most of the patterns are that way. Value object is not. The idea behind a value object is that there's some objects that don't act much like an object. You're not so concerned with identity. They don't really keep state. Actually, you want to make them be immutable. You create the object, and once it's created, it never changes. So if we think of doing mathematical objects, whether you have big numbers, for example, the big numbers might be implemented by an array of integers, but you don't want to be able to go in and just arbitrarily modify pieces of them. Usually we want the strings, because it's useful to have strings that you can edit, but it's also useful to have immutable strings, strings that you know can't be changed. And so there's a lot of times where we want to have these objects that represent values. One of the things about them is that equality is always important. So if you have values for the different colors, say, you want to know if two colors are the same color, and maybe you keep there's like three cyan and magenta, and I forget what the third color is, and you keep a different, so it's a trio of colors, of numbers, and you can compare if all three of those are equal, not whether it's the exact same object. A date, to say we've got two objects that each say they are the 7th of October, 2010, they're the same date, even if they're different objects. So you want to implement equality for them. Now, turns out that there's lots of different places where this pattern is useful. So it is, because you don't have side effects, it is useful in parallel programming, where you want to share values between processes. If the processes are mutable, if the values you're sharing are mutable, then you have to worry about synchronization. If they are these immutable objects, then you don't have to worry. You can share them very easily. When you're talking to a database, you want to write values out to the database, make them persistent, read them back in. If they have state, and you have to worry about it, you have to have IDs and keep track of identity that way. But if you have value objects, you only have to have some way of printing them out or serializing them, and you can read them back in. Distributed programming is another case. There's a lot of places where having value objects is useful. It is, we actually knew this was important, and a number of people had tried to write this pattern early on, and we never put it on the list of patterns we wanted to write in the book, but at the same time that we were trying to write the book, I was trying to write the value object pattern, and I just didn't like what I wrote. It just didn't seem to me it was describing things. I know that Kent Beck tried to write it, and he didn't like what it was. A lot of people tried to write it. The first person to write this pattern in a way that is generally, is the way people think about it, was Eric Evans in his book, Domain-Driven Design. But now we have an example of how to do it. It's going to be a lot easier to write it in a form that fits in with design patterns. It is sort of different from the other patterns, but is a very core one. And null objects are very simple patterns. Like I was looking in design patterns, if you look in the iterator pattern, there's a place that talks about with an iterator, it's useful to have a null iterator. That's exactly applying null object to the iterator. So design pattern already has, you might say, citations to this pattern without actually saying it's a pattern. So when we start doing related patterns in the book, that would be very easy. And there's many other places where you could put null object in. But null object is a very simple pattern. I think there's been a conference on patterns called PLOP, Pattern Languages of Programs, PLOP. That's been since '94. That was the first one right before the book came out. So they both came out of the movement to write about our patterns. And so we had the four of us working on a book, and then lots of other people saying, let's have a conference, and we can all be writing patterns and sharing them. And I don't know if this was the very first plop. I think it was the second plop. In '95 was when somebody wrote about this pattern. So it's been well known. So it's a very simple pattern. If you see code like this, where you have to worry about null. You have to worry about null. And so we were saying, well, if it's a null, then we do this. Otherwise, we do the real thing. But you have to have a check for null. What you do instead is say, suppose we made a separate class of whatever the class of OBJ is, an interface. OBJ is an interface. And there's maybe many classes with that interface. Let's add a new class that's going to have that same interface, the interface of OBJ, and we're going to call it the null whatever this class is. It's going to be our own special null object with this interface. And then, instead of writing this, we can just write that. We just call this, and maybe OBJ will never be null. OBJ might be a pointer to this new kind of null object, which has that interface, so we can just call. So it's simple. If your code is littered with these tests for null object, you do this little transformation, and your code gets much simpler. But the other side is, then you can do more interesting things to handle the null. So it gives you a. So what's going to happen then is you had a class hierarchy. So we said we have parts, and we have composite parts. So there's some classes that do the composite pattern. There's another pattern is decorator. When you can use composite, you can usually use decorator. They fit together very nicely. So there might be several patterns you can sort of, and there'll be classes, of course, that are just your classes that do the work. The simple classes that you need. They'll be in here too. But what you'll do is you'll make a new class with a null object pattern, which is your null power, and that eliminates a lot of error handling that you will see. And a related one, and this is a question, maybe we really shouldn't call it null object, maybe we should call it like exceptional object. Generalize it a little bit, because maybe you'll have things that aren't nulls but are different kind of errors. And so it'll be an issue when we put it into the book of just how general do we want to make that pattern. Should we call it null object? Should we call it exceptional object? But it's the same idea. It's the same idea that you're going to have a special class that has the same interface as everything else. It's very key, have that same interface, but you're going to put error handling in that class rather than spreading it all through the program. So this is not necessarily a category of patterns, because mediator is one of our core patterns, and singleton is a creational pattern. So there are already categories for them. But it is a fact. It is a fact that there are certain patterns that people seem to misuse a lot. And when you go out and you Google some of these different patterns, especially singleton, you Google singleton, you'll probably have 9 out of 10 people telling you how bad it is. Okay? And the things they say are generally all true. They're not making things up. They're not misunderstanding singleton. No, they're saying true things about singleton. But mediator is another one, and both of these patterns were ones that people latched onto pretty early. They'd read the book, and they would sort of see how they could use these patterns, but they weren't necessarily using them in the right way. And I believe that the reason, a lot of the fault lies in our book, because we didn't explain the dangers enough. It's not really that the patterns that people often say, like singleton is bad and you should never use it. Well, maybe that person should never use it. There are other places where it makes sense. You sort of have to know when to use it and when not to use it. We clearly did not explain the dangers of it enough. You can't argue with that, because so many people misused it. Now, but that's true of mediator as well. So the mediator pattern is supposed to be a pattern about reuse. So you have a class hierarchy that you think is going to be nice and reusable. But every time you try to use it, you discover that you have to add a little code to this class, a little code to this class, and a little code to that class. And the reason is because these classes have to communicate in some way. And after like the 5th time you come in, and maybe you aren't editing the classes, maybe you make subclasses of them, but you're just making all these different subclasses, and you didn't think you'd need to make so many subclasses. What's going on here? What you realize is that this way that objects interact is something that needs to be changed. And so what you'll do is you'll add this new object. You'll put a new object in the middle of all these other objects, which represents, in some sense, the way the objects interact. And every time you use them, you will make a new mediator object. Mediator objects are always ugly. They always are just a bunch of code that make things work. So we shouldn't be proud of our mediator classes. The purpose of the mediator class is to make the rest of the classes be reusable. So when you do it that way, it's good. But what you often see, and at least this is especially true 20 years ago, when a lot of people were coming to object-oriented programming who were experienced programmers but just didn't know object-oriented programming. They would be coming expert procedural programming. What they would do is build lots of very, very simple classes. They were really just records, just held data, and then they would have one really complicated class that would control everything else. And that's a mediator, which in some ways you could say it is a mediator, but it was not making the rest of the classes be reusable. It didn't really have that purpose. If you look at the diagrams of the mediator, it seemed to fit. And so there's a case where we didn't describe the purpose well enough and describe the dangers of ending up with one very large class that had all of the complicated logic in it. And the same with the singleton pattern. The singleton pattern encapsulates global state. Now, everybody, if you have not that much experience in programming, you all know that global variables are bad, right? Global variables. Everybody knows global variables are bad. Well, the singleton pattern, you can basically have a global variable without having a global variable. You can hide your global variable inside a singleton. Now, if you understand why global variables are bad for a number of reasons. There's basically it's coupling. You end up with two parts of the program can communicate with each other through the global variable, and you can't see that communication. It makes it hard for you to tell. And when you use them a lot, basically every part of your program is communicating with every other part of the program through the global state, and it makes the program very hard to change. It makes it hard to test. It makes lots of things hard. So, when I said that the people who are criticizing Singleton are correct in their criticisms, I'll back up a bit. When I was looking at them, and like 3/4 of them were saying Singleton is bad because it makes your program hard to test. Well, yes, but to me it makes it hard to reuse and hard to change. And the way we write tests today is basically by writing clients of the code. We're writing some code that's testing the rest of our code. So tests are really just one way of reusing our code. And yes, it makes your code hard to test, but it makes a lot of other things hard. And so when you're suppose you're building an embedded system. It's going to be a controller for the transmission system of tractors or cars or something like that. Well, it's usually a small number of people who program that, and there's not a lot of reusable code in it. You make one version for this car, another version for that car, another version for this car. You tweak the code each time, but the way that people build those things is more specialized. In an environment like that, the singleton pattern is not so bad because it's a small group of people and it all fits together. Now, where people complain about the singleton pattern is in something like you're doing a big enterprise Java application, and so you have lots of people who are working on it. There's lots of libraries you're reusing, and the problems of the singleton pattern become pretty overwhelming on those kind of projects. So. Again, the book does not describe that. It does not describe the dangers of it at all. So I'm not trying to justify that Singleton is a good thing, but there are places where it's pretty useful. And I use Singleton in Smalltalk. Smalltalk was always, although there's a group of people who made it, it was sometimes a single programmer environment, and it was always small teams of people, and there were maybe 4 singletons in Smalltalk, 3 singletons, a pretty small number of them. I started hearing people doing stuff in C++, a team of 100 people. 100 people, we got 100 singletons in our system. It was very bad. So these are the creational patterns. So there were these 5, and Singleton, it was sort of a non-creational. It's about you only want a single object. You don't want to have You want to have a single object in a class. So the others, at factory method is about having a method that creates objects for you, and abstract factory, prototype, and builder are about having an object that creates other objects for you. Abstract factory doesn't actually get used as much. Having factory objects is bigger than any one of these patterns. It's a common thing to have an object that makes other objects for you. To delegate the creation of objects, to package it up. And builder and prototype and abstract factory are each a particular way of doing it, but there are other ways to do it as well. One of the things that has gotten to be popular and the very term for this is something in the past 20 years is dependency injection. So how many people know what dependency injection is? Okay, slightly less than half. Anyway, it is. Now that once I learned what it meant, I said, well, I guess we did that in Smalltalk too, but we didn't have a name for it. But the idea in dependency injection is that you want to make all your components so that they only depend on interfaces. They don't actually name the classes that they're creating. You don't have factory methods in them that will create others. Instead, you could perhaps pass a factory in to let them create things. That would be okay. Or you have a whole layer on top where you specify what the concrete classes are, you create your instances, and you plug them all together, and then your classes, basically the constructor is told what the concrete classes are that you're going to be interfacing. Now, in the Java world, there are frameworks like Spring where you can have XML files that tell you what the concrete classes you're using and how you're connecting them together. And you can not only eliminate the need of some of these other patterns, but often you can avoid having a singleton because you can make an object at this higher level and pass it in as well. So there's a lot of things that this dependency injection can do. And that's something that we realize ought to be, there could very well be other patterns that ought to be in the creational as well. So that's one that we're planning to do. So the peripheral, we had, so like visitor is one of the patterns that the most papers are written about. People who get into patterns really enjoy visitor. It's hard. I think it's probably the hardest of all the patterns. Some of the patterns are really very simple. Visitor is not simple. And when you learn visitor, there's usually, when you first look at it, it's like, how can this work? And then, aha, I see how it works. Something sort of clicks in your brain, and it's sort of the pleasure of solving a hard problem. And then, of course, I want to use this on a problem myself. And in fact, visitor is not, there aren't very many cases where visitor is the right thing to use. Okay, so a lot of times that visitor is used, it's used incorrectly. It's used by somebody who's very enthusiastic, who wants to figure out a program that they can put it in themselves. And there's this sort of this learning process. I think with all patterns, where the first time you use it, you have like a 50% chance of using it right. And but with visitor, people don't ever get a second chance, I guess. There's a lot of misuses of it. But it's very cool, and in some areas, I do a lot of work with refactoring tools. If you're trying to build a compiler in an object-oriented language, if you're doing language processing, it's very useful. And so it's a great pattern for those type of applications. But in your typical business applications, it's not that useful. I know that there's some 3D graphics packages use visitor well. So there's various domains where visitor. I mean, it's not like it is a real pattern. It is a real pattern that has useful properties. It's just sort of a more rare pattern, and it's not really criticism against it. It's more popular than it ought to be because it's cool. And if you think of it as an educational device to teach you about polymorphism, I'm going to learn that because the real object gurus all know how visitor works, and I want to learn how visitor works too, so I can really understand object-oriented programming well. Then that's good. Just don't think that your program has to use visitor, because it probably doesn't need to use visitor. Bridge was very common in C++, and for some reason not very common in Java and in Smalltalk. not entirely sure why that's the case. So that's something we need to explore more about why that hasn't been more common. I think a lot of it was that purpose of bridge was to solve some of the problems and the rigidity of the C++ type checker. A chain of responsibility is a nice pattern in the sense of easy to understand. There's certain places where it's really useful. 90% of the time, maybe 80% of it, that seems to me like the a very large percentage of the time that a chain of responsibility is being used is when you're also using composite. And so a composite forms a tree, and chain of responsibility is when you're going up the tree. So the pure composite, when you ask the composite to do something, it asks its children, and they ask their children, and it sort of comes down. That's sort of the pure composite. But chain of responsibility is when one object asks another, and it says yes or no, and you ask the next one, it says yes or no. You keep going, passing the responsibility until you get to an object that says, oh, I'll take care of that for you. And maybe you go all the way to the end of the line, and nobody will take care of it. That could happen. But you're hoping that some object will take care of it. And like I said, chain of responsibility is easy to understand, but maybe we should have just called this something that composites do. The number of times when you're doing a chain of responsibility without composite, this is a question, should it be peripheral, should it be core? One of the things I like about chain of responsibility is its name. So most of the patterns have names, so like Memento is one of these that I haven't, but if you go back to Observer and Composite, these names are named after one object in the collection of objects that's doing something. The pattern is more than just one object. Composite is more than just a composite class. It's about the interface they all share. It's about the various the components that you put in the composite. They're all necessary. You can't have composite only with a composite class. You have to have all the rest of the classes too. And that's true of all these patterns. They're more than just a single class. And yet we name each one after one single class in the pattern. And that annoys me. I like to have a name that somehow tells me about the whole pattern. And chain of responsibility is a wonderful name. So I'm a little, that's a other side of how important that is. So type object, if you talk with people and heard about adaptive object models, it's a very important pattern there. Extension object, that's something that Eric Gama really likes. That actually, Eric Gama was one of the key architects in Eclipse, and so actually Eclipse uses this fairly heavily. Generation gap was something that John Vossides liked. It's about code generation, how you generate classes to separate reusable code from the code you write by hand from the generated code. John Vossides, one of the sad facts of the world is that John Vossides passed away half a dozen years ago, and so when we do a second edition instead of if, and it's something we keep saying we're going to do, it's going to have to be without John, and so we'll leave his pattern in there. So the compound patterns, two of them are the two that are patterns in the old book that we're saying, where should they fit? And the two that we're going to put in the class of compound are flyweight and interpreter. So many people who are pattern experts will say, I'm not sure if I've ever really used flyweight on a real project. That's a pretty narrow one. And what happened in that book with the IBM Smalltalkers was that they gave several cases of flyweight, and the four of us all said, no, that's not flyweight. No, that's not flyweight. Because in each case, they were just doing a part of what flyweight does. And flyweight has a lot of parts. It has a lot of parts, and often people would just do a couple of the parts and say, oh, this is like flyweight. And probably we should have described flyweight as a set of different patterns. And then you can say, if they all get combined like this, then you get the properties of flyweight. So, flyweight is about saving space. So to save space, that's a key part of flyweight, which people, I guess, book doesn't make clear enough that that's the purpose behind it. Most of the patterns in the book are about reuse, about making software be more flexible, about making it easier to change. Not quite. Flyway is not about making your software easier to change. What happens, though, the reason why we saw Flyway in these reusable class libraries is that you keep making your objects more and more flexible, and you make them smaller. You make them smaller and smaller and smaller. After a while, you get billions of little tiny objects that all look the same. And it wastes a lot of space. And then you can use this technique to save space. So this is actually related to value objects, because part of it is you have objects that you think of as having state, and we're going to split them into two parts. Part of it will be immutable. Part of it will be these value objects that are immutable, and then the other part is the part that actually changes. And when you make all these value objects, you might as well not have two copies of a date, say. Say dates took a lot of space. If dates took a lot of space, let's suppose you had an application that was going to, well, we're going to do all of history of the last 2,000 years, and so we have billions and billions of events, and they all have these dates on them, but, well, we've got only 2,000 years, and yet we've got billions of other places that have dates, so we can factor out those years into something factor out the dates into something smaller. Anyway, that's sort of the idea. You have to have a factory that you go to say, build me this date, or build me this whatever, and then the factory looks up to see if it's got one already. If it does, it gives you the old one. Turns out this is very similar to a singleton. So you could actually say that a singleton is sort of like a special factory that keeps track of some limited set of objects, and if you go and you ask it to make an object like this for me, it looks to see if it already has one. If it already has one, it gives you an old one. It doesn't make a new one for you. Now, singleton only has one. That's very easy. It either has one or it doesn't have one. It doesn't have to do much checking. And so, like I said, we can think of a flyweight as having all these different parts to it, and the purpose of that is saving space. The interpreter pattern is that you are thinking of something as a program. You basically want to represent an expression you're going to evaluate, or a program you want to execute. And you build it up as a tree, abstract syntax tree for all you people who had compiler courses. It's the same thing. And then you want the class hierarchy of the composites to match the grammar of the language, and then you can have this operation on every class in that hierarchy that is able to interpret. So anyway, you can look at this as just something built on top of the composite. Now, when we wrote design patterns, one of the questions we often had was, is this pattern part of that pattern? And we didn't ever want to talk about that. When you look at the book, there's not a lot of discussion of relationship between patterns. What we'll say is, often when you use this pattern, it will often be useful to use that pattern. But it's not a requirement by any means. Early on in the book, we thought of writing the abstract class. We thought of writing abstract class as a pattern. Now, if you program in Java, abstract class is like a keyword. If you put abstract on your class to make it, it's built into the compiler. The language has a notion of abstract class. That's not true of C++. Some people think it is. I can argue with you about that. It's still a design idea, and certainly in Smalltalk, a lot of the older object-oriented languages, most of the older object-oriented languages, do not have abstract class built into the language. It's a technique, it's a design idea, it's a way of using it. And so it's a pattern, because that's a pattern too. But if we had written abstract class as a pattern, then almost every other pattern in the book would use abstract class. And we really did not want to talk about patterns can be made up of smaller patterns, and they can be linked together in this way. That just was, we wanted to just talk about patterns. Now, there's another book patterns of object-oriented software architecture, POSA people, by people from Siemens, 5 Germans from Siemens. And it had, that book came out just a year or two after our book, and they actually were planning to write about a lot of the same design patterns we were going to write about, but they realized we were first. We were going to publish before they did, and so they had to redesign their book, and so they reduced a lot of the design patterns. They still had some design patterns in it, but they emphasized much more that you have, they call them idioms, which are more language specific and even lower level than design patterns. And they sort of had design patterns in the middle, and they had architectural patterns up at the top. And they talked about how one type of pattern could contain another type of pattern. All this is true. And I think it's fine for them to talk about that. We really didn't want to talk about that in the book. But second edition, I think we'll have to talk about that more because it is true. It's a fact of techniques that we build up complicated techniques that are made up by composing simpler techniques. It's what people do. It's what people do. So I'm trying to go over some different issues with the book, and I described the composite pattern for you. One of the things that the composite pattern does, when you get to this issue about adding and removing, how do you add and remove? There's basically 2 choices. You can either say leaves are going to have add and remove operations. This is composites do. But if you actually try to call add and remove on a leaf, you should get some error message. And the other approach is say, no, only composites have add and remove. And then, when you're going to want to call add and remove, you have to do like a type case. You have to downcast from component. I've got some component, and I'm expecting it to be a composite, so I have to do a downcast from component to composite so that I can call the add and remove. That's your choice. You either could put add and remove just in composite, or you can basically put it on component, have implementations both in leaf and composite, and have these generate error messages. Well, the book says that the right way to do it is to put the interface in component and then have leaves generate error messages. And I disagreed with that at the time, because in Smalltalk you don't do it that way. In Smalltalk, you just put in add and remove, and of course it's all dynamically typed, and so there's no official downcasting. But this is when you write your code in such a way that you make sure it really is a composite, something that can be added. Then you add the component or remove the component. And but the C++ class libraries all did it by putting add and remove in the component. So I lost because there were 3 C++ programmers to 1 Smalltalk programmer. So the book says the other way. Now, the interesting thing is, to say 5 years after the book came out, when you look at the C++ libraries that have been coming out in the past few years, they were doing it the way Smalltalk did it. They were only putting add and remove on the composites, and the reason was that just at the time that design patterns came out, C++ added type-safe downcasting to the language. That now you really could do a check and see what the type was, and you couldn't do that in the old C++. There wasn't any way to do that safely. So the only way was of course the book doesn't say, well, if your language is like this, and this is how you do it, and if your language is like that, that's how you should do it. We didn't understand that. It was a simple vote, which one is best, and we said, okay, this is the way it should be best. But right now, of course, there were arguments that I lost where it turned out they were right, and I don't remember any of those. Right? I remember the argument I lost when I was right, of course. But that's because things happen. You learn more as time goes on, and this is sort of the case when when the book should be revised. So there's a lot of other things in the book that should be revised. in some cases, so like this refactoring, the relationship with refactoring. So I had started working on refactoring and writing some papers on it, but in fact, everybody who wrote the book agreed at this time. So what I'm saying is not really controversial. It wasn't like we wrote the book and I lost the arguments. It wasn't like that. The problem was that most people out in the programming world at the time the book came out didn't really believe in refactoring. There were lots of people who thought you should think very hard, design things up front, and do good, and patterns fit into that. And so we didn't want to annoy them and make them dislike our book. So we didn't really want to emphasize. So we talk about how there's a section on refactoring, and we talk about how you can have these patterns in mind from the beginning, or later on in the life of your program, you can discover that you need the patterns and you can put them in later. But in fact, my belief, and certainly the belief of Eric now, and I think it was really his belief at the time, was that usually you want to keep your program simple. When your program is simple, it won't need very many design patterns. Design patterns are really more valuable as your programs are complicated. And as time goes on, you'll see the need for your patterns. And so you change your program. You refactor your program to put patterns in later. And that's really the best way to use the patterns. It should not be thought of as things that you do before you start writing code. There's a book, Joshua Karievsky has a book called Refactoring the Patterns, where he goes through each of the patterns and talks about how you can see the need for this pattern in your code and then change your code to use the pattern. And I think that, so there have been cases that I've worked on a system in one programming language, and now I'm going to go build something very similar in another programming language. And I remember the design in terms of the patterns that are in it. And then I can just sort of write the patterns from the beginning, because I've already done it before, right? I'm remembering the design. I'm not creating the design. So in cases like that, you can just sort of use these patterns as code generation templates. But normally, that's not how it works. Normally, that's not how it works. So again, it's something that the book works hard not to say, because we didn't want to offend people who were in the majority 20 years ago. Now, something that we never thought people would say was that people they look at a program and try to count how many patterns are in this program. And the bigger the number, the better the program. They're using counts of patterns as a metric of goodness of a program. And so the other side of that is, you are a programmer, you want to make your program better, let's put as many patterns in as we can. Now, when people do that, then it almost never results in better programs. And the thing is, patterns aren't, they're techniques that can be useful, or sometimes they're not useful. So when they are just count the number of patterns doesn't count. So when I teach course in design, one of the things I like to do is give programming assignments where I will tell people, I give them a program and I will say, put this pattern into the program. And I do it knowing the pattern will make the program worse. And because people need to experience that and see that the patterns aren't always making things better. And part of it, again, if you go off and you start to say, I'm going to learn about these patterns, I'm going to try them out on all the programs I write, and that's a good way to learn. That's a good way to learn. You will just naturally use patterns where you shouldn't use them, and when you're all done, you'll look at it and say, oh, that was not a good idea. Now, if you say, oh, the observer pattern is a bad idea, I should never use it, that's a wrong lesson to learn. Means that that was clearly not a good use of observer pattern. I wonder what I should have used instead. I wonder when observer should be used right. Those are better questions to ask. You can trust the fact that hundreds of thousands of other people have used observer and liked it, to be that probably there are some cases where it will be useful, but it doesn't mean it's going to be useful in this program like it. So that's, and then why do we use patterns? And the book doesn't talk about this enough. Heads First Design does a pretty good job of talking about design principles, relating each pattern to certain design principles. I think design patterns should do that. That's one thing. I'm not going to put crossword puzzles in it like Heads First Design did. But that idea of linking the patterns to the particular design principles that they illustrate is great, and that's something I would really like to do. So you look at different purposes of patterns. One of them is that we want to change our program. We want to have some aspect of it changed, and so we break that out into a separate component, and then we can replace one component of that interface with another. So the strategy pattern, you have a lot of different strategies. You can replace one with the other. The observer pattern makes it easy to put new observers into the program. So this is related to decoupling. Obviously, it's easier to vary if they aren't coupled with each other. But often decoupling is variability management. You have a much stronger idea of exactly what can change. You've got a series of things you want to change. Whereas decoupling is more a matter of that people will be coming in and making changes to this code later, but you aren't really sure what it's going to be, and you're just trying to make it easy. Keep there from being too much coupling between this part and that part. Dependency management is more about like compiling or testing, being able to test one component without interfering with another, breaking your system up into smaller pieces so that you can test them individually, you can build them individually, you can test them individually, you can then put them together. Anyway, I can make a much longer list of things, but knowing the purposes behind the pattern, and the patterns usually aren't only for a certain purpose. They are techniques people have developed. They can be used in a variety of things, but not just in a. And then, of course, the real means you're trying to make your programs be easier to manage, easier to understand. It's not how many patterns you put into the system. So I guess I sort of said this already about patterns being examples of principles. I think it would be better to do that. There's an idea that's in the people who write patterns have this idea of a pattern language. And a pattern language is the language that an expert or a community uses, sort of the language of patterns that they use. It's all the patterns that make up this particular design style. It's a design style of a person, design style of a community. And so when people write patterns, they often are trying to write a pattern language for something. So Joe Yoder has got a paper that he's working on now, a pattern language of test-driven development, where it's what are the different reasons you write tests. And we've got a bunch of different patterns for the different type of tests, the different reasons you would write a test. So something people have always asked is, well, these design patterns of yours, how do they fit into a design pattern or a pattern language? How do they all fit together? And they really aren't. They're not a pattern language. The book makes very clearly these were not a pattern language. This is just a catalog. It's a bunch of patterns. We're not really sure what order you do them in, how they fit together. Don Roberts and I wrote a paper years ago called Evolving Frameworks that tried to describe it. And what we said was that the patterns don't come in when your programs are simple. They tend to come in after you start building up a library, you start trying to reuse them, and you see these things that need to change. And so variability comes in. And it's after that that you will start applying the patterns to make your objects more reusable. So, but this sort of big question: where do design patterns fit into the overall design style? And that's something a book ought to talk about. And to tell you the truth, I think there's a lot of this is old paper, and there's a lot more rethinking that can be done. So any book that's 20 years old can be criticized. There's bound to be lots of things wrong with it. I'm actually starting a series of talks that are, I'm looking in detail at things that I see that are wrong with the book. And that's the great thing about the internet. You can Google any pattern, you can find all sorts of people that will tell you things are wrong with it. But there are things wrong, as you'd expect with age. But on the other hand, it really is something to be proud of. It has a big impact on the world. And the key idea behind it is that there's more to programming than just programming languages. There's more to programming than algorithms and data structures. There's all kinds of knowledge. There's all kinds of knowledge that we use. We were really only looking at a small part of that knowledge. But if we're really serious about programming, about understanding programs, we need to understand all this kind of knowledge. And so that's the value of the book. We took a category of knowledge that nobody was looking at before. There really wasn't anything like this before. And we did our best to write it down, which of course we're not perfect, so there's lots of things wrong with it. We've got a lot of people to help us do it, which I think is also really key. When you want to do something right, want to do something as well as you can, don't try to do it all by yourself. You can always do better when you get help. So if it's really important to you to do it well instead of just doing it yourself, get help. Taking exams, of course, you're not supposed to do that. But we all know, we can see from exams the value of how it would be to get other people to help us. And outside of these exams, it really is more important to do it right than it is to just do it yourself. And we should get other people to help us. So the Hillside.net is Hillside is the group that sponsors these patterns conferences and has a lot of the people in the group are people interested in patterns. So there's a lot of material here for people who are interested in patterns. But I'm very happy to answer questions about design patterns or pretty much anything else.
I'd like to say that at the conference that Ralph Nation is blocked, the Pattern Language of Programming conference that happens every year in the United States. In Brazil, we have the Sugarloaf block. But now it happens every 2 years, and that's why Ralph is here, because we were in Alabama for the last edition. And the next edition will be 2 years, so hopefully some of you will write your own patterns in your own domain and will submit the Sugarloaf block to you, or maybe this one.
Do you want to also tell people that on Saturday there's a workshop in the morning? I think still people next to
Yeah, there are. So Ralph will do workshops here at TV Saturday morning. There are limited number of places available. Maybe only about 10 slots left. If you are interested, how can they find? Ask me. Ask our place. Write the code at TV.com. Okay, questions, please.
Actually, I have one. I'd like to hear more out what was like to develop software before those design patterns. I mean, Hammond probably came up with them to solve some real life problems.
Okay, so the first thing is we didn't invent any of these design patterns. So John thought he invented Visitor, but other people did it before him, and so eventually we realized that. And I think all the rest of them, we never thought we invented them. They were things we saw and we copied, and I wrote a paper on the state pattern, and that was the first time anyone wrote a paper about that. But we had seen that code elsewhere, and we were copying it, and I think that's typical of some of those patterns we had written stuff about as we discovered them and we got excited about it. But they all were things. So what happened was as we were writing the first version of the book, Addison Wesley got a bunch of people to review it, and some of them were really experts in object-oriented programming, and some of them were experts on software but didn't know much about object-oriented programming. And the people who were experts in object-oriented programming said, "Oh, these are all good things, but we're not sure whether there's enough information here to actually communicate it to people who like don't know it already. And the people who were not experts in object-oriented programming, many of them were senior people, they said, what's this about? So the first group was right, and we made it like 3 times longer, put tons of code examples in, and did all this stuff to get it across. So the question of, well, what was programming like? Well, programming was, in such sense, there's been other things about programming. Like one of the things that has, to me, the number one thing that's changed programming the most is having the internet and having search engines. You have a problem, you just go Google it. You had to figure everything out yourself. And young people that can't really imagine, I think, because if you learn to do it properly, my son is a programmer. He graduated from college a year ago. So he learned Google in 7th or 8th grade, and his whole life has been, if you want to know something, you can just go look it up. And once you start to learn the programming, it goes the exact same way. Some of the undergrads at the University of Illinois haven't seemed to learn that, so I know that not everybody knows how to do that. But the fact is, you run into some programming project, some airman, Google that thing, and it's amazing that 9 times out of 10, somebody else has had the same problem and will answer it for you. So to me, that's a bigger difference than the design patterns. Because the design patterns they help you learn faster. They sort of, but I learned design patterns not by reading a book, but by reading code. And people can still, if you read the code that has them in, you still are going to learn them all by yourself. You don't have to have them. It's faster to have the book, because it sort of tells you what to look at, but you're going to learn them anyway. And the other thing is that now you have a language for talking. So it definitely has made communication among experts more efficient, because you don't have to go down and talk about all this low-level stuff. Oh, I see. I did that on this project here. That's what you call it. And now you can communicate. Instead, you have this vocabulary, we start doing this and this, and everyone sort of expects you to know it, and so you can communicate in a more efficient. So that's one of the places. But just the the book itself is, in some sense, it's a library. That when you read the book and it tells you these techniques, you then go off and read and use these libraries, and that enforces it. It's having that whole culture of things out there, and object-oriented culture. So when I started, you had Smalltalk, which was very object-oriented. There were a couple other systems that were object-oriented, but there really were very few object-oriented systems. And Microsoft and Apple and all those places, IBM, they really weren't doing object-oriented programming at all. And then by the end of the 90s, object-oriented programming was clearly taking over the world. All the new things were being object-oriented. And now, when people start programming and it's just sort of object-oriented programming, they never learn anything else. Object-oriented programming is programming. There isn't any other way of programming. Well, I actually think that's bad, because there's, in fact, lots of different kinds of programming, and it's good to know different styles of programming. And there's plenty of stuff that object-oriented programming is not the best way to do it. But if that's all you know, then that's what you're going to like. Often I've done stuff object-oriented because I wanted to learn what object-oriented programming was good at and what it's not good at. And the way you find that out is you use it for things it's not good at. There's no other way to learn what something is not good at other than by using it on things it's not good at. So if you're trying to explore, then you use it for everything. But anyway, so that's one of the main differences now, is that when I started, object-oriented programming was weird, and now it's normal. And that's pretty different. And I mean, it's both good and bad. It isn't entirely good. Yes?
These problems seem to be pre-theoretical constructs.
Yes.
There's no theory from which
They are pre-theoretical constructs. There is no theory for generating them. Absolutely true. There's no theory for generating them. And so one of my first slide was about a lot of the awards the Patterns book won. And one of them I think is strangest is the SIGPLAN Programming Language Award, because it's not a book about programming languages, it's a book about programming. Not languages, object-oriented obviously, but we could throw any object-oriented language. Our claim is Java had not been invented when the book came out. Java had not been invented. Our claim, if you had told us there's going to be a new language next year that's object-oriented and is like this and this, we would have said, oh, design patterns would be great for it. That was it, because it's just like these other languages we've looked at, and so the same patterns are going to work. And we were right. These are patterns that use in Java all the time. So it was very much looking at what was there already. So one of the things that design patterns had an impact on theory was you used to have these people doing type theory and program verification of object-oriented things. And they would say, and we want to deal with inheritance. And they would come up with some examples for inheritance. And the classic example was you have a 2D point, and we're going to make a subclass, which is a 3D point. We're going to add in sort of a Z coordinate to your X and Y. And every time I read this, like, that's not what people use inheritance for. That's a horrible example. Well, after the book comes out, they take the composite pattern. And now composite is what and the other theoreticians, right? They want someone else to give them examples and they'll run their theory through and they'll figure out how it works. And when they get better examples, they produce better type systems, better program verification systems. So there is a sense in which we are characterizing, but we're not doing it from a theoretical point of view. We're doing it from an observational point of view. We are looking at what people really do and things that seem interesting, things that are hard for newcomers to understand, the unusual parts. The patterns are not, like you might say, normal. It's not what everyone was telling you to do before he wrote the book. It's the things that are a little tricky. It's a little unusual, and that was. But again, they're common. They're not the normal thing, but they come up over and over and over again. So there must be some reason for them. We don't always know the reason for them. We give reasons. Right? Humans are incapable of seeing something and not trying to justify it. We have to come up with some excuses, right? Some reasons for it. We're not always right about our reasons. And that's a place for theoreticians now to come in and say, why are people doing this? Or what are some better ways of doing this? And it's certainly fine for people to try to find better solutions to the problems these patterns solve. Yes?
So, thank you for the warriors that places in design patterns was the need to the code for maybe some people have a lot of solutions around that. I would like to ask you the access of design patterns, the addition of code quality. You said simple small programs, not the code all. What you were talking a little bit about how you
How would I measure code quality? Well, the ultimate. So the question is, if counting patterns is not a good measure of code quality, now what is a good measure of code quality? How would I measure code quality? I mean, my measure of code quality is that I look at the code and I try to read it, and how long does it take me to understand it? But of course, I also expect to be able to ask questions to an expert and to read documentation. So better documentation to me means better code because I can figure out the code better. And you also you're trying to make a change to the system. How easy is it easy to make a change? But these are pretty human. I mean, none of them are directly related to metrics of numbers of classes or depths of inheritance. And again, my experience is like other people. When you look at some class that's got depth of inheritance of 12, this is going to be a pretty tough system here. But Joe and I both are fans of reflection and these meta-object things. And that's a sign of systems that are hard to understand, too. So there are, the ultimate measure of goodness is going to be, you might say, human-related. Things like how easy is it to understand, again, how easy is it for me to understand versus how easy for somebody who's been programming for 3 years to understand. Very different questions. And then there's ease of changing, but there's all different kind of changes. There's like the normal change of a customer comes in and says, I don't like the way the screen works, let's change the screen, versus, okay, you've got it running on Android, now we want to run on the iPhone. How easy is that going to be? This could be a pretty difficult. So there's all different, even this issue of how easy is the change is hard to measure. But the real important ones, the metrics, are these human-oriented metrics. We come up with code-oriented metrics because they're easier to measure. and they're not really as useful, but because they're easy to measure, we do those measurements.
We have been waiting for the second edition. Do you think we'll be able to see it within the next 2 or 3 years?
Probably not 2 years, maybe 3 years. I mean, I am trying to start the process, but it will. And so one of the things, and this is like other people who are doing patterns. Sometimes people just write some patterns because they're going to get a paper out the door and then they'll go on to something else. There are people who write patterns and they really are hoping that they're going to get used for a long time. And I think one of the mistakes we made was that we didn't start a process on day one to do a revision. We should have been planning that 5 years out we would have had a revision. Every 5 years we would do a revision, do something like that. And if we had started that, then it would be we'd get the 5th edition now or something, and it would be a very, very different book than it is. Yes.
Your patterns, they usually have side and conceptual part. They usually have an implementation, suggestion of an implementation. So for example, observer, we usually notify all observers when something happens. But what if I have some rule to decide which one should be notified? I mean, if I change the observer, I have a different implementation of observer. Should I call it an observer or should I not?
Okay, so the question is, how much can you change a pattern and still keep it the same name? And this is a general problem anytime you make definitions and you have categories. And there are, when you look at people's opinion, there's sort of 2 types of people. We call them the lumpers and the splitters. The lumpers like to put everything together in one big category and talk about how all this stuff is really all the same. There's all these variations maybe, but really there's one key idea. Whereas splitters like to have lots of different names and lots of different categories, and it seems to be a personality difference. Now, I think I tend to be a lumper in the sense that I think that you can vary a pattern a lot, and I also think, oh yeah, it's still observer. So, for example, in Java, we have listeners. The very first version of Java had they called it observer and observable. So observer was the interface, observable was a class. That was Java 1.0 had that, and they were doing the user interfaces with it. Very quickly discovered that doing observer by the book, by our book, wasn't the best fit for Java. They came up with listeners, observer, listener. Sounds pretty similar, right? But the key idea in listener is you always have an event object. So there's always this event that gets created. Now, when you read the book, we talk about how you can pass various information around, but we don't tell you anything about it. And I'm pretty sure that I had seen Smalltalk systems back when we wrote the book that had event objects and were doing things that way. There's really no hint of that in the book. Nevertheless, from my point of view, I think of listener as just the Java way of doing the observer pattern. All the design issues that you have to worry about, notification and update, and you have to implement the way it reacts, it's all exactly the same. The way Java does it fits into a strongly typed language when you want to reuse better. Java or C++ was strongly typed, but they didn't really have reusers. No standard libraries at all. Smalltalk wasn't strongly typed. It wasn't statically typed at any rate. So it had more reuse. So anyway, there was I consider listeners to be an example of the observer pattern, and that's one of the ways that pattern should be rewritten so that you can make that clear. It should be talking about passing event objects around, and you can hold the information you need in the event objects. But I can see that somebody else would say, no, that's a different pattern because it all depends on your point of view.
Any last question?
I'd like you to comment on how the evolution of the software architecture in the last year since the book was released, how this affects the content
how does the evolution of software architecture in the last few years affect the context? I mean, that's way too big of a question to answer, because of course there's lots of different ways it's been evolving. I mean, you can look in the Java world, and there's things like having libraries like Spring and dependency injection, and that gives you those makes those patterns cheaper. That that's influenced what people have done. I mean, a whole other way of looking at it is that an awful lot of people don't really program at a low level. They're taking big packages and putting them together and writing a little glue code between them. So they are going to live with whatever patterns people put in those systems. They're not going to be interested in these type of patterns because these are more patterns of building the libraries. But for most of those libraries, they're still done in object-oriented languages. If you look inside the libraries, you're going to be seeing these patterns. So I suppose if you are the sort of person who's taking big stuff and plugging them together and writing adapters, you're writing glue code, and glue code, like adapters are a typical type of way of writing glue code, then these patterns might be helpful for you to learn the packages and what you have to do to them, but you're not going to be deciding whether you use these patterns because that's already been decided for you. And of course, there are like a functional programming people. That's sort of different styles of programming. But in the same way, back when he wrote the book, most software was being done in COBOL. So these patterns had very little to do with Fortran and languages like that. And these patterns didn't have too much to do with that software. So again, there's plenty of people out there writing software in other styles, and you don't expect the patterns to necessarily fit them. Which is why people should write books on those other styles of patterns. So one of the things, though, I believe that all humans, and this idea that you use some technology, and the technology gives you low-level things, and after a while you figure out certain combinations of these low-level things that are useful for you, you're creating these patterns. And that happens whether you're designing software or airplanes. It's going to happen when people are doing genetic engineering. They're going to have patterns of gene combinations. I mean, this sort of patterns is what humans do when we're designing. We're given low-level stuff. You figure out interesting ways of combining it. And if you really want to teach a technology to people who are practicing, who are doing it, we want to study how people build things. We want to come up with names so we can talk about it. We want to break it down. And the divisions, the categories you make will always be approximate. They'll never be perfect. People always do things sort of halfway one way and halfway another way. My standard example is the state pattern and the strategy pattern, because both of them, when you look at the diagrams, they look pretty similar. And there's an object that points to an abstract class with a bunch of subclasses. And there are things I can say, well, this is what is always true of state, and this is always true of strategy. But what happens when somebody writes a program that does half the things on state and half the things on strategy? And there are programs like that. There are programs like that. They say, well, what is it? Is it state? Is it strategy? I'm not sure what it is. Well, the real question is that a good design? Does it solve their problems? And now, of course, then if you say it is a good design, then you have to explain it to people, and you can say sort of half like state, half like strategy. It does this like state, this like strategy. And to people who know state and strategy, that's good enough. It doesn't have to fit the book. You're trying to make a good design. And patterns, like I said, are something that humans do. You learn a little technique, and then you do it over and over again every time you come across a problem that's like that. You'll try out the stuff you know how to do, the stuff that you know works. I had eye surgery recently, and doctors have these patterns that they follow, things that they do, and they tell you these different techniques. I mean, it's just human. This is the way humans solve problems. So technology evolves, and the patterns are going to evolve. But to some degree, it's that we just get experience with them. People read the book and do stupid things, and we know, I didn't describe it very well. Or sometimes the world has changed, and so it's actually things are actually different from. There are more alternatives and different things than the book might have explained 1994 pretty well, but it doesn't describe 2014 very well. And other things are still the same, which is actually interesting how much has stayed the same in 20 years. So any more?
So Ralph will be here a few minutes if you want to talk first.